Okay, John.
Okay. Okay. Uh, well, thank you very much for the invitation to give a talk in this, Pacific Quasiworld seminar. And the title of my talk is a little bit different, but it's the content is still the same. And I'm sorry, maybe one third of the people here had already, heard almost the same talk. But for most of the people, this is a kind of new subject, and I have to return to the beginning always. So my talk is on the construction of Sobolev spaces on metric spaces. Okay, and in particular, the Sobolev spaces on fractals, in particular self-similar sets. And on the self-similar set, like Sierpinski gasket and Sierpinski carpet. So we have studied analysis on fractals, and what we have done is, construct the diffusion processes, or we may say the construct Laplacians, and analyze the asymptotic behavior of heat kernels, or the spectrum of Laplacians. And this type of analysis corresponds to the analysis of W12 Sobolev spaces. Okay, because there is always behind the diffusion processes there is a quadratic forms called the Dirichlet forms, and the domain of the Dirichlet form is corresponds to the W12 Sobolev space. Okay. And so on the smooth space, like R to the N, so the definition of the 1P Sobolev space is, this one. And that is, F is in LP Rm. And this nabla F is, of course, the differentiation with in the sense of distributions, okay? And this, nabla F to the P, and to make the integral all over the space. And, this value is called the P energy of a function F, okay? And W1P Sobolev space is the function whose P energy is finite. So how about the case of metric spaces? So this is the case of, the Sobolev space, and this definition uses, derivation and differentiation, And so that in the case of metric spaces, the classical idea is, okay, let's think about the Lipschitz functions, okay? And so for the Lipschitz functions, by definition, we have, this type of inequality. So that we can define the local, Lipschitz constant in this way. So think about this is a ball with radius r, and think about this value divided by r, and take a supremum all over the ball, and take the rim sup, so the r to 0. Okay, and this is a kind of local Lipschitz constant, and so this is a counterpart of nabla of U. Okay, and so instead of using the nabla F, one can use this value, and actually, so the generalization of this local Lipschitz constant is called upper gradient. And under this idea, so Highwash, Chiga, and Shamringham, and they have defined some kind of Sobolev spaces on metric spaces. And there are actually 3 different definitions. But nowadays, we know for the good spaces like the space having the volume doubling property or other properties. So these three spaces are the same. Okay, and this is a classical, theory of Sobolev spaces or metric spaces. But recently, so Kajino and Murugan showed that for the Sierpinski carpet and the many other self-similar sets, this idea won't work. Because the simple reason is, the domain of the dirichlet form is there is no repeat functions in the domain. Okay, so we need some new kind of definition of Sobolev spaces for these self-similar set, Sierpinski carpet or other self-similar set. And our idea is, the basic idea is very simple and primitive. Okay, so let's think about the case of the unit interval. This is the unit interval. And let's divide the unit interval to the, to the n, intervals. Okay, and then, think about the discrete P energy. Okay, so this is, so f is a function from 0, 1 to r. And think about this, difference between these two vertices, okay? And take an absolute value and to the piece power and make sum them. And then, by the kind of elementary calculus, one can show that, if f is smooth, or, more generally, if f is W1P space, you know that this discrete energy times this scaling factor go to the P energy of the function. Okay, so this is the case of interval. So the idea is, okay, so this is a discrete approximation, discrete P energy here. And okay, and then find some proper scaling factor and take a limit. So we might find some, P energy on the space. That is the idea of construction of Sobolev space, or I mean that's P energy. So what I said was, okay, let's in general let XD be a compact metric space, and let approximate this XD by a sequence of graphs. Okay, so in this case, in the case of interval, the graph is like this one. These are the vertices, these are the vertices, and these are the edges. Or, this is a case of Sierpinski carpet. Okay, so and these are the vertices, and these are the vertices, and these are the edges. Okay, and this is the first step, and this is the second step. Okay, so in general, let's think about some graph approximation of the space, and then on this graph, discrete graph, we have discrete version of the P energy. And so our problem is, so are there any good scaling factor here? So that's this scaled, P energy convergent to something. This is some broad mean of convergence. Okay, convergence to some nice value. So and so the problem is this space with some nice sigma is rich enough. Some, contains rich functions and some, good properties. Okay. So this is a problem. And what I want to say is, so in this construction, we will not care about the counterpart of the, gradient. So we don't use the notion of derivation. That's quite different from this method using upper gradient. Okay. So there are several questions, two questions in particular. So, sorry. So when does this strategy works? So the answer is notion so-called conductive homogeneity. Okay, and this is a condition for general metric space, compact metric spaces. And then, so what are the examples? Are there anything new or anything interesting which satisfies this conductive homogeneity? Okay, and well, actually, I want to talk about mainly about this examples, but before that, I have to explain what is this, and and well, actually, this is some crazy part of so my dream is actually reconstruction of analysis, not starting from derivation. Okay. Well, this is a crazy dream, I know. So so this is a discrete graph, and so actually for the case P equals 2, and P equals 2 correspond to the construction Brownian motion, or the diffusion process. And in this case, for the construction of the Brownian motion on the Sierpinski carpet, originally, Barrow and Bass constructed the Brownian motion through scaling limit of Brownian motions. But later, Kusuak and So actually constructed the Dirichlet form of Brownian motion through the same idea as ours for the case P equals 2. So they investigated when the two energies, sequence of discrete two energies converges, and constructed the local regular Dirichlet form on two-dimensional planar generalized Sierpinski carpets. Okay, but since now, there are no examples with even for the construction of the Brownian motion. We couldn't construct the diffusion process on this type of non-symmetric, cell set. But due to this, work, now we can construct the Brownian motion on these spaces. Or the other example is which I call the regular polygon-based locally self-symmetric cell sets. And this is a joint work with Yuka Ota, who is my PhD student. And the new examples are this is a cell set based on starting with the triangle, and this is the starting from pentagon. And you see, this has full symmetry of pentagon, but this has no symmetry of triangle. And other new examples are so this is a hexagon based, but the symmetry is smaller than the symmetry of hexagon. And this is octagon based, okay. And this one also has a smaller symmetry, the symmetry is the rotation group of 90-degree rotation. Okay. And so if I will have enough time, I want to talk about when this type of self-similar set has conductive homogeneity, or we can construct the P energies on this set. And actually the answer is, my answer is, if there is no obstruction, and I don't, I think I won't have any time to give a definition of the obstruction. But anyway, I have to explain. So what is conductive homogeneity? Okay. So, and before that, so to set up the framework, so I need first to establish the graph approximation of the space. And to do so, I will use the notion of the partition of a space. And this notion partition corresponds to the dyadic cubes in harmonic analysis, actually. And the idea is very simple. Okay, so first we have the wall space, the XD. This is X, actually. And the first step, we will divide this space into several pieces. And in this case, the 3 pieces. And next step, we will divide this, K1 into several pieces, and K2 into several pieces, and K3 into several pieces. And, and then next step, we will divide, for example, this piece into several pieces, okay? And I will assign the symbol phi to this first step. And the next step, we have 1, 2, 3. And next step, we have 1, 1, 1, 2, 1, 3. And this S1 means a kind of, the children of 1. The 1 is divided is 1, 1, 1, 2, 1, 3. So the construction is, for every step, we divide. So every step, so for the former step, we have W. For example, this W is 2. Then for the next step, we have some SW, so S2 here. And KW, this space, is a union of, the K21 and K22. And, keep going in this way. So roughly, this is a notion of partition of a space. And for the Sierpinski carpet, or the self-similar set, we have a natural partition with space. So for example, the case of Sierpinski carpet, so as the first step, we have, there is 8 contraction mappings for the Sierpinski carpet. So we have 8 symbols, and we have 8 pieces. We divide the space into 8 pieces. And the next step, we divide this 1 to 8 pieces, and so on and so forth. Okay. So this is a natural partition of the Sierpinski carpet. And then we think these pieces of partition as the vertices of the graph. And how we will set up the edges. So we set up the edges if 2 pieces, for example, this K2 and K1 as an intersection, then we will have an edge here. So, and then, so this is the second step of the graph. The dotted lines are the, dotted lines are not vertices, but this is edges, sorry. Let's see. Okay. This is edges. Okay, so now we set up the graph, and so here is some notation. So this is the graph distance of the, Tn, En. And graph distance just means that if you have, for example, so this one, so the distance between this one and this one is the length of minimal path. I mean, in this case, the minimal path is this one. So that length is 2, okay? So this, so 2 steps here, so that the length is 2, okay? And this gamma MW is the M neighborhood of the W, okay? And so let me, in this case, in the case of Sierpinski carpet, at this level, okay, this is W. Then the one neighborhood is these pieces, okay? And this, for this V, 2 neighborhood is the pieces which can reach here in 2 steps. So that's, this piece actually has intersection here. So that this is 1 step and 2 step, okay? And this red region is the 2 neighborhood. Okay. And then what I will define next is a kind of ball with radius something. So X is now as a point in the space. And this set is a union of K V's. And what is, so first we will find the W's, vertices, which include X, and make all the union of the M neighborhoods, okay? So for example, for this X, X is included in these 3 pieces. And then think about the one neighborhood of this piece, and this piece. And the union is actually this region. And this is U1, X1. So a kind of one neighborhood of this X at this level. Okay. And so we need some, good relation between this partition and the original metric. And the standing assumption on my talk is, okay, there is this UMXN is actually a neighborhood of, C1Rn or C2Rn. So I say that R to the N, that the neighborhood of X with the length R to the N. And so this UXN can be compared with this, neighborhood with respect to the metric D. So this is, standing assumption of my talk. And you can easily see in the case of Sierpinski carpet or the nice Selshina set, one can easily check this condition, okay? So under this, assumption, so I will define the conductance of, first, this is the discrete energy of a function f on, Tn. So this is nth level approximation with space. And so this is a kind of the energy of the part of A. A is a subset of Tn. And the energy of the discrete P energy of function f on this part A is just, for every vertices included in A, we, sum up the difference between this Fw and Fb to the power P, okay? So this is the P energy. And then what I will define is P conductance between A1 and A2. So the setup is Okay, so A1, A2, and A is a subset of Tn. So this is A, and this is A1, and this is A2. And and there's another parameter, M. And M is a parameter which defines this space, this graph up to the n plus m level. Okay, so these are the tile set of n level, and these small ones are the n plus m level. And what I will do is, okay, let's think about the function f, which is 1 here and 0 here. And think about the p energy of this function f as the n plus mth level, and taking the inf of this p energy for all the functions satisfying this. And this is the p conductance between A1 and A2. Okay. And so, and using this p conductance, I define the conductance constant. And the definition is that think about some w here, and think about the w and the complement of the m neighborhood. So in this case, this is w, and this is the one neighborhood, and this red region is the complement. Okay, and think about the conductance between w and this complement, and divided further into mth level here. So this is the conductance between W and its complement, and define the EMPW, which is supremum of all this value through the all vertices at every level. Okay. And actually, what we can show is this value to the 1 over m has a limit. And actually, this value Rp is closely related to the geometry of the space.
So, Jun, sorry to interrupt. What are the assumptions on your space here? The space is doubling, right?
Oh, yes, space is doubling, yes.
And anything else?
Well, there are some small, additional conditions, I suppose, but, essentially the volume doubling and connected.
Okay. Yeah. That's fairly general. Okay.
Yeah. And so, well, I don't remember exactly the assumption of Carrasco and Piaggio, but it's the same as the Carrasco-Piaggio's assumption. Okay. And so Carrasco, Piaggio, and the Kleiner has a result that if their result was using the modulus of curve, discrete curve families, but I just related it into the energy version. Okay, so the what it says is if Rp is less than 1, if and only if P is larger than this R-force regular conformal dimension. And what is the R-force regular conformal dimension? So that is the infimum of alpha, so that there exists a metric rho on X, which is symmetric to the original metric D. And there is a measure mu, and which is alpha R-force regular with respect to rho. Okay. And okay, so alpha R-force regular means, not mu, but so the volume of the ball with radius R is comparable with R to the alpha. Okay. And naturally, in this case, so if we have this one, so the half of dimension of the space is alpha. And what is the Kaji symmetry? And I suppose many of the people in the audience already know the notion of Kaji symmetry, but well, I think I have 20 minutes left, so that's I just say that Kaji symmetry means if two metrics are Kaji symmetric, that means uniformly bounded distortion of annuli. Okay, so of course, if you have two different metrics, the annuli are the distorted, but this distortion is uniformly bounded. So that's roughly the notion of Kaji symmetry. So that this R-force regular conformal dimension is, think about the metric which has bounded distortion with respect to the original metric D, and which is, so there is some measure which has alpha R-force regulation. And so, and infimum of such alpha is R-force regular conformal dimension. Okay. So, and this is and there I need one more constant, which is called neighbor disparity constant. Yeah. And this is actually a variant of the Poincare constant. Well, it looks a little bit different, but it's a kind of Poincare constant. And for the case P equals 2, this constant was introduced by Kusuoka and Cho's paper. Okay. And the definition is if there is a 2W and B, which is next to each other and has an intersection, like this one, then think about the function on this space. I mean that this is SMW is the mth refinement of W. And in this case, I write the second refinement of the space. And think of the function on this space. And this is a difference between the average over here and the average over here. And average means that, okay, we assume there is some nice measure and, and the average with respect to this measure. And this is, okay, so, and this is average over here, and this is average over here. And think about difference and to the P's power divided by the energy of this value, this function f, okay? And this is, and taking all the, supremum of all these bodies as nth level, this is called sigma p mn. And let's take the supremum all over n, and this is called sigma p m, okay? And what we have free is that this relation between the, this is the conductance constant, and this is neighbor disparity constant. And we always have there is some C0, which is not, larger than 0, So this value is uniformly bounded from below. This is always holds. So this is free. So the notion of the conductive homogeneity, which ensures the success of our construction of Swirl space, is that, actually I say that this is free. And the conductive homogeneity means the other direction is also true, okay? So, and so why this is called homogeneity? Because if we
Jun,
have
sorry,
this.
sorry. I see. Yeah, sorry.
Okay.
Yeah. Okay.
Yeah. So this why this is called homogeneity, because under this conductive homogeneity, what we can see is this value. This is the value before taking the supremum. Okay, before taking a supremum, for each W we define this value. Okay, and what we get is if we have this conductive homogeneity, then there is some nice sigma p. This is a constant. And this behaves like sigma to minus m uniformly with respect to W. And also this conductive, the neighbor disparity constants behave like sigma p to the m. And you remember that originally there is n, which is, thinking only about nth level of the graph. But despite, independent when this sigma p and m behaves like this. So this is, I call this homogeneity. Okay. And under the, this conductive homogeneity, and we also, well, in this talk, I also assume that P is larger than R for regular conformal dimension. Okay. And then, and if X is a P conductively homogeneous, we have a nice, space WP. And the definition is, here is this is a scaled version of the discrete energy. Okay. And PMF is a LP function. And PMF is a suitable, discretization of function F. So this is a discrete energy, and this is a normalized factor. And well, here.
Sorry, what is the measure here? The measure mu?
Measure mu is some measure which has a volume doubling property.
Okay.
Okay. So, and in particular, in the case of Sierpinski carpet, naturally, I choose the natural measure with the celestial measure. Okay. But in general, it's a volume doubling measure. And we will see that actually this notion of conductive homogeneity is independent of the choice of measure later. Okay. Because this value, well, despite this part, this value is, there is no measure here. Okay. And so taking this NPF, and this actually NPF is a seminole. Okay. And this is NPF is a substitute of P energy. Okay. And WP is a space where this P energy is finite. Okay. And then actually this space with this is LP norm plus this seminorm is a reflective blank space. And actually the part of reflectivity is due to the Schmitt's result. And WP, if P is larger than the alpha cellular conformal dimension, this WB is actually embedded in the continuous function. And this embedded map is actually, of course, continuous. And also, the functions in this space has some Helder continuity with this tau p order. Okay, and this tau p is actually determined by this scaling factor and this R. And what was R? So where is it? I suppose here. Oh, here. Okay. So here is the assumption that this, neighborhood is neighborhood with radius R to the n. So this is the kind of contraction ratio of the space. Okay. So we are here. Okay. Okay, so, and in particular, if the P is 2 and R4 conformal dimension is less than 2, and X is 2 conductive homogeneous, then we can replace N2 by E2, which is the regular local judicial form, okay? And which is so-called the resistance form, and we have a nice diffusion process on the space which satisfies a nice heat kernel estimate. Okay. So that's, for the case of planar Sierpinski carpet or, planar selection asset, we naturally have this condition. So if we have if space is too conductively homogeneous, we have a nice diffusion process. And so the problem is, okay, let's see. So we only talk about this case. P is larger than the alpha regular conformal dimension. So what happens if, the P is equal or less than alpha regular conformal dimension? Still, I know that this space is a Banach space, and this WP is dense in subset of LP. But, I don't know that this space, WP with continuous functions, has, how large it is, I don't know in general, And I don't know, are there any elliptical Harnack principle for p-harmonic functions? But for the case of Sierpinski carpets, so in particular for the planar Sierpinski carpets, so Murugan and Smith has, solved these problems, and it is okay now. So, and their paper actually have, original paper has 160 pages long, so it's very dedicated work, actually. And other conjecture was, actually, this was a conjecture, and actually this was solved. But, as I told you, in the case of if P is larger than alpha regular conformal dimension, so my space, this WP is embedded in CK. And my conjecture was, this is if and only if. And so actually this was solved by Kao Chen and Kumangwai in recent paper. And they show that if P is less than equal this region, there is an unbounded function, LP function, contained in WP, okay? And so if you remember the Sobolev embedding theorem on the ordinary space, so you see that, on the ordinary space, so this dichotomy, there is the same dichotomy. I mean that Sobolev space is embedded in continuous functions or not. And the criterion was, the ordinary, the dimension of the space. And so this says that, for the case of the general metric space, the ordinary dimension n is replaced by alpha regular conformal dimension. Okay. So now we have a nice criterion, which is called conductive homogeneity. And the problem is, so how can we show this conductive homogeneity? So that is the one of the big concern. So even if there is a nice condition, so we need many, plenty of examples. Okay, and so the one of the condition is this one. So this is again. The case P is larger than alpha regular conformal dimension. And in this case, this condition says that, okay, let's pick up any W tilde, okay? And think about the conductance between W tilde and M neighborhood with the level M, define this part with further M's level. and compare this with this one. So this one is, okay, let's think of another W, which is not related to W Tudor, any W, anywhere. And think about the case level of refinement. And this is a case level of refinement of W. And pick up any 2 here. And divide and think about the conductance between W and B, further nth level, okay? And so what I require is this 2 value can be compared with this constant, which only depends on this K. Okay. So, and this condition, I call it the night move condition. So originally, in the case of the construction of the, the Brownian motion on Sierpinski carpet, so they have, Bar and Bass have some condition called the night move condition. And this is quite different from the original night move condition, but it still has some speed. Okay. So now the problem is comparison between 2 different, conductance between 2 different spaces. And and also please notice that in this condition, here is no, the neighbor disparity constant. And there is no measure in here. So what I write here is conductive homogeneity is determined solely by conductance constant. So it's, well, if we change the measure, we don't change this condition. Okay. And this is the reason why I just call this conductive homogeneity. Okay. And to show the conductive homogeneity, actually, night move conditions, we use the modulus or combinatorial modulus of passes. And so, well, I don't have only 2 minutes, I think, and I should move quickly. So that's, this is well, this is a graph, and taking A1 and A2 here, and this is all the passes between, passes on the graph between A1 and A2, and this is the function, the so-called admissible functions. Okay, so f is a function on the graph, and the condition is, for all the passes, sum of this value is larger than 1. And the discrete modulus of between A1 and A2 is actually the infimum of the LP norm, LP P energy of function of the admissible function. And the important point is that this conductance and this modulus are comparable. Actually, there is C1 and C2 is always comparable, so that we can replace the notion of conductance by this M. So we can use some geometric argument to estimate these values. Okay, so I just say here that and skip some part and go to the final part. So, well, this is the example which has the conductive homogeneity. And so this one, I call the Murugan, or, and this one has some kind of, some global symmetry, which is the 90-degree rotation. And this has a symmetry of with respect to this line. Okay. So, and so to show the conductive homogeneity at this level, we need some local symmetry and global symmetry. And this is other examples. And no longer we don't have any global symmetry, but we have local symmetry. I mean that, for example, this one, let's see, here is two pieces, which has a common line here. And these two pieces has a symmetry with respect to this line. This is what I call the local symmetry. And as you see, let's see, like this one. Oh, where is it? So this one, like, well, let's think about this part and this part. With respect to this line, this two part has a symmetry. So, and such kind of figures, I call that the self-similar set with local symmetry. And I have some theory when this kind of self-similar set has conductive homogeneity, but I don't have any time left. So thank you very much for listening.
Yeah, thanks, Jun. So let's thank the speaker. So are there comments or questions? Well, so let me ask. So you said, I mean, the ambitious goal of these investigations is to somehow recreate analysis in this context. So what are the next steps here?
Oh, what are the next steps? Oh, well, of course, you know, the natural next step is to construct this NP, which I constructed, is very rough. Where it is? Yeah, this NP is very rough, but I know we can, you know, replace this NP by more, you know, natural object, like, you know, have a Markov property or the local property. Okay. And actually, Kajino and Ryosuke, you know, Shimizu, recently developed the theory of this type of, you know, Sobolev space on what the nested fractal, so-called nested fractal, which is a kind of variation of the Sierpinski carpet. And what they have done is actually they constructed not only the P form, but the P, and not only the P energy, but P form. And so that they could extract some kind of P Laplacian there. Okay. And so the first natural direction is construct the P Laplacian and the P harmonic function, and you know, and so on and so forth. Okay.
So in the chat, there are two questions. So the first question is, which papers should one look at if one wants to learn more?
Oh, well, so my theory is in this paper. Okay. So this is Memoirs of the European Mathematical Society. Okay. And other papers, you know, for example, let's see where it is. This one. So for the, well, actually, so for this, for the works on the Sierpinski carpet, so let's, you know, find the Murugan and Schmidt's paper. I suppose their paper is on archive. And they have actually two versions, longer version and shorter version, because they prepared the shorter version for submission for some journal. Okay. And also, you know, if you look at the name Shimizu, Ryosuke Shimizu at the archive, then you will find, you know, the Kajino Shimizu's recent paper. Okay. So that's a way how you can find the related papers.
Okay. So there's one other question. I'm not sure whether I understand it. The question is, what is capital SC? May I have a look at the first page? I'm not sure what this is supposed to mean.
First page?
Sierpinski carpet?
Oh, Sierpinski.
Oh, yeah. Sierpinski carpet, yes. Yeah. Oh,
Yeah,
sorry,
on the
SC
very
is the
right
Sierpinski
here.
carpet. Yeah. So sorry, I forgot to explain it. Yeah. So this is a discrete approximation of Sierpinski carpet, and well, afterwards I only say SC, but write SC. Yeah.
Oh, I see. Yeah, I didn't even notice this. Okay, are there other comments or questions?
I have a question. You might have mentioned this, but maybe I missed it. Do we know what's the relation of this type of Sobolev spaces with other notions of Sobolev spaces under certain assumptions, perhaps?
Actually, for the case of the Rn or the cubes in the Rn, general cubes in the Rn, it's the same, which I showed in my paper. Okay.
I see.
And the case of the coincidence with this theory, I don't have any proof, but I suppose in some case, so for example, for Chiga's paper, they assume some 1p Sobolev, not 1p Poincare, inequality. And in such a case, my conjecture is my construction and their construction is the same. And actually, let's see. So now there is a paper by Ryosuke Shimizu. Yeah. And he actually compared my kind of construction with the collaboration type construction.
Mm-hmm.
And so it's and he showed that there is a collaboration type expression of the Sobolev space, our Sobolev space. So that through this collaboration type construction, we can compare these spaces and our spaces. Okay.
I see. Thank you.
Yeah, other comments or questions? Actually, I'm looking at the list of participants here, and it so happens that Stephen Keith is there. And this was
okay.
the point that I wanted to make. Jun, you credited Carrasco, Kleiner, and yourself for
yes.
I think you should have mentioned Stephen Keith here as well, because I think this was joint work with Kleiner that was never published, I think.
Okay. So I'm sorry. I had some mind. Okay, so Kleiner had some co-author, but I have completely forgot the name.
Yeah, we haven't seen Stephen in a while. Hi, Stephen. How's it going?
Hi there. I didn't want to take up too much attention here, but yeah, thank you. I appreciated the talk. I enjoyed the talk.
Yeah. Well, I wanted to see you actually. You have many good papers, and I never saw him. Okay, it's very nice to see you.
Apologies for that. I appreciate I appreciate your presentation. Thank you very much for that.
Yeah.